Section 13.1 Vector Fields, Video 5, Gradient Vector Fields. Recall from a previous section, 11.6, the definition of the gradient of a function. In two dimensions, if you have a function f of x, y, its gradient was the partial derivative of f with respect to x as the component of I, plus the partial derivative of f with respect to y of xy as the component function for j. In three dimensions, it was the same thing, except your function was a function of x, y, and z, and you have a k component in your vector, or a k part of your vector, whose component function was the partial derivative with respect to z. So in general, take a function, partial with respect to x is the component of the I, partial with respect to y is the component of the j, and the partial with respect to z is the component of the k if it's in three dimensions. So really, when you saw the gradient previously, it was just a specific example of a vector field, a function that takes a point in a plane or a point in space and turns it into a vector. Such a vector field is, of course, called a gradient vector field. So for example, let's find the gradient vector field of the multivariable function f of x, y equals x squared y minus y cubed. So our vector function f of x, y, vector f of x, y, will be the gradient of little f, which is the partial derivative with respect to x, that will be the I component function, plus the partial derivative with respect to y, that's the j component function. The partial derivative with respect to x is 2x squared y, and then with respect to x, y cubed is a constant, so its derivative is 0. So 2x squared, the partial derivative of x squared y is 2xy. And for the j component function, we need to take the partial derivative with respect to y. With respect to y, the partial derivative of x squared y is just x squared minus the partial derivative with respect to y of y cubed is 3y squared. I attempted to go into the Desmos vector field generator to illustrate this vector field and relate it to the, what's the word I'm looking for? To the level curves for this function. Remember, we can't sketch this in two dimensions because it would require three variables, an x, a y, and a z. But we can sketch representative curves by letting this equal a constant and then sketching that as that graph each time we change that constant. But I'll just read to you really quickly on page 759 what it does say about this vector field relative to the level curves you can generate for this two variable function. And this is on page 759, so you can get a visual. On page 759 in figure 14, we have a contour map of f, which is just graphs of this function equal to a constant. And superimposed on top of that is this vector field. And the relationship is that the gradient vectors are perpendicular to the level curves, which, if you go back to the 11.6 discussion, shouldn't surprise you. And that the gradient vectors are long when the level curves are close to each other and short when they're further apart. In other words, think of it this way. Let's say that this measures the height off the ground of a point, like a topological map. Then all the points that would be the same height off of the ground would be connected. So what does it mean when two curves are close to each other? For example, let's say that this represents 10 feet and this represents 11 feet. Well, it doesn't take too far to go up a foot, and so the directional derivative would be larger because, well, if I'm going from 10 feet to 11 feet and it only takes me that short distance to go that far, then our directional derivative here would be pointing in the direction of maximum descent. But if the level curves are far apart, like if this were 12 feet, if this were where the function was equal to 12, then we would expect the directional derivative, the gradient, to be shorter because it took a long time to get from 11 feet to 12 feet. So if this were 11 feet and this were 12 feet, and it took us, well, let's use an equivalent scale. If this were 12 feet up, and this were 11 feet up, and it took us this long to get there, then our directional derivative would be shortened. So I'm not sure if I believe what I just said about that last part. My point is, on page 759, they give the visual connection between the level curves for this function and the gradient field. Yeah, that sounds good.